Hello, my name is Ray, and I will be doing a differential equations problem. It's a first-order linear differential equation that we will solve using variation of parameters. Here's our equation, and actually it is a IVP. It has an initial condition, so it really technically should be an initial value problem. Again, we'll be using variation of parameters to solve for this. So if it's a first order linear, probably the best thing to do in the beginning is write it in standard form, which says that we should get y prime by itself, and we will divide everything by x minus 1. So we're going to get y prime plus 3 over x minus 1 times y is equal to 1 over x minus 1 to the 4th power, because we're dividing out by x minus 1. So we throw in another factor of x minus 1 in the denominator. And then we have a plus sign x over x minus 1, again increasing the factor by 1, so we have it to the 3rd power. Okay. Now this method of the variation of parameters says that we have to take a look at the complementary equation, and that complementary equation is the equation y prime plus 3 over x minus 1 times y is equal to 0. So we're going to go from a non-homogeneous to homogeneous differential equation, and solving for this will help us solve for the rest of that, the non-homogeneous portion, and that is by using the variation of parameters. All right, this is a simple separable differential equation. We will rewrite y prime as dy dx, and then we will bring this other term over to the other side, so we'll get a negative 3 over x minus 1 times y, and then we will separate the x's and y's. So we're going to get a dy over y on the left hand side, and then we're going to get a negative 3 over x minus 1 times dx on the left hand side, or on the right hand side. We will integrate from here, and it's nice because the differentials are already all set up. This is going to be the ln of y, and this is going to be a negative 3 constant ln of x minus 1. The plus c here is not going to matter, and I think maybe even the x minus 1 business. Normally we would find the absolute value of this, but we'll leave it as such for now. And I think we're going to need to use some laws of the logarithm to be able to simplify this a little bit, because we generally want to solve for y. We're going to get the ln of x minus 1 to the negative 3 power, and so we get y is equal to x minus 1 to the negative 3, or 1 divided by x minus 1 to the 3rd. Okay, this is our solution to the complementary equation, and we actually will end up calling this y sub 1. And that was our first step in the variation of parameters. The next step is that we're going to assume that our actual solution to the actual differential equation, the non-homogeneous differential equation, is equal to some parameter u that we're going to vary, hence the name variation of parameters, times the solution that we found for the complementary equation, which is y1. Okay, so that's the y1 that we will eventually use, but we'll set this up first. And as we set this up, we'll see something interesting happen that will happen all the time. And so you can find a little shortcut here, but I would suggest that you go through this process all the way through. All right, now we want to put this solution into this equation up here. So we'll need y prime. So let's find y prime right here first. And this is a product of u and y1, so it's going to be u prime y1 plus u times y1 prime. And let's put that into this differential equation now. We got y prime, which we just found to be u prime y1 plus u y1 prime. And then we have a 3 over x minus 1 times y, but y is equal to u times y1. And then this, for now, let's call it the right-hand side, because I don't want to keep writing this until we're ready to actually incorporate it, because right now we want to focus on the left-hand side. And if we arrange the left-hand side and write this as u prime y1 plus u y1 prime plus 3 over x minus 1 times u times y1, regrouping the second and third terms, we will see that this is equal to 0. Wow, why is it equal to 0? Well, let's put the right-hand side here for now, and let's talk about why this is equal to 0. If we factor a u out, what we get is a y1 prime plus 3 over x minus 1 times y1. That is exactly the complementary equation, and we had just proclaimed that y1 is a solution to this complementary equation, so that means this whole thing should be 0. Even that u out there will be multiplied by 0, so that whole thing disappears. So that simplifies our left-hand side, which means now we can rewrite this as u prime y1 is equal to, plus 0, is equal to the right-hand side. So now let's write the right-hand side. And the right-hand side is 1 over x minus 1 to the 4th power plus sine x divided by x minus 1 to the 3rd power. Okay, now let's solve for, well, we want to find y. We have y1, but we don't have u. So we will solve for u. And at this point, we get to put in our y value or function. I get u prime is equal to, or times, x minus 1 to the negative 3 power, and that's equal to 1 over x minus 1 to the 4th times sine x, or plus sine x, over x minus 1 to the 3rd. And this is 1 over x minus 1 to the 3rd power, so we can multiply that on both sides, and we will get u prime is equal to 1 over x minus 1. So all 3 of them go away, and we have one factor of x minus 1 left. And for this last one, the whole denominator goes away, and all we have is a sine x. Remember that we want u, so we would integrate with respect to x. And in doing so, we will get u by itself, which is what we're looking for. And now let's take the integral piece by piece. The first one is going to be the ln of x minus 1. And I think I do want to put that absolute value here at this point, because we're getting close to the solution. The antiderivative of sine is negative cosine, so let's put a minus cosine x, and then we have an arbitrary constant c. So this is the u that we were looking for, but remember the actual solution is y. Y is equal to u times u y1. So this is going to be equal to ln of x minus 1 minus cosine of x plus some arbitrary constant times the u1, or the y1, sorry, which is x minus 1 to the negative 3 power. I suppose we can simplify that, and we'll call this our general solution. general solution, and the general solution is going to be y, and then we have the ln of x minus 1 minus cosine of x plus some unknown constant divided by x minus 1 to the third power. Okay, so this general solution, we would be done if we didn't have an initial condition, but we do have an initial condition, and our initial condition is y of 0 is equal to 1. So let's go ahead and use that initial condition. And that initial condition will help us solve for c. So this tells us that x is equal to 0, y is equal to 1. And this is a good thing that we found this to be, found the absolute value there, because, you know, we're going to get a negative number in the ln, and that would be bad. So to use this initial condition, we will take the general solution, put 1 in for y, and then we have the x's. We're going to put 0 in for all those x's. And we have cosine of 0 plus c unknown, and then 0 minus 1 to the third. Okay, let's simplify this. This is ln of absolute value of negative 1, or ln of 1, minus cosine of 1 is 1, plus c divided by, this is negative 1 to the third. And so this will give me 0 minus 1 plus c over negative 1, so that would give me a positive 1 minus c. And this is equal to 1, so c must equal to 0. And when c is equal to 0, we have our particular solution. Particular solution for this IVP, the initial value problem, and that is going to be y is equal to everything here, x minus 1, ln of x minus 1 minus cosine of x, but this time instead of a plus c we got a plus 0, so I'll just leave that there, and we have an x minus 1 to the third in the denominator. So this is it. That's our solution. It would be interesting to look at this in from a graphical perspective. So let's take a look at the slope field. Let's box this up first. All right, let's take a look at the slope field. This is a slope field for this particular function. Remember, to draw the slope fields, you have to go a step further in your equation and not just solve for the prime and with the y, but actually solving for the y prime by itself. So if you solve for the y prime by itself, you get this right-hand side, and then you need to also subtract out this portion of your expression. So we have this negative 3y over x minus 1, and then this whole thing constitutes the right-hand side after we divide it by x minus 1. So this is a slope field that we get. Notice there's something weird happening when x is equal to negative 1. There's nothing there, and that kind of shows that our solution here has an x minus 1 in the denominator, so when x is equal to positive 1, there's nothing happening. In fact, that's probably something that we should address. Well, we'll address that in a minute. But we found this solution, right? So I restricted it at some point, but let's just keep it the way it is. Oh, let's first talk about the general solution. So this is a general solution for different values of c. When c is equal to 10, I get something like this. When c is equal to some number 1.3, we get another interesting dip in the curve here, and curve goes up. when c is equal to something like -10, it looks like just a regular asymptotic rational function, which we know it's not because there's a cosine involved. So that is generally how it looks like. That's your general solution for different values of c. But we want in particular a c is equal to 0, so we put c is equal to 0. We get this, and this is the solution that we found for c is equal to 0. Now, this solution looks like it has two parts, but it looks like it splits when x is equal to 1. So the existence and uniqueness theorem actually tells us there's some issues happening here when we have an x value that's undefined. So we'll note that y does not exist when x is equal to 1. So that factor of x minus 1 in the denominator makes it undefined there. So the solution must be in one of two possible intervals. And we cannot have x is equal to 1 as a solution. So it has to be either going from -infinity to +1, or it has to be going from 1 to +infinity. Okay. Now, your initial condition has an x is equal to 0. That's your initial condition, x is equal to 0. So x is equal to 0 is sitting right here. So your interval must be going from -infinity to 1, which means in our solution we have a graph that breaks off at x is equal to 1 and something to the left and something to the right, but we know that this cannot exist on both sides, and so our existence and uniqueness theorem tells us that we need to restrict our solution to go from -infinity to 1 and not look at the positive part. Now I can't do -infinity in Desmo, so having a really big number here like 100 is probably good enough, and this is exactly what we're seeing as our solution. Okay, so that's it. We have our solution, we have our given interval based on the existence and uniqueness theorem, and we have solved for this problem using the variation of parameters. I hope that helps. Good luck.